So I apologize, I did this a little out of order. I'm going to hold on and not show you how to integrate exponentials base e's just yet. I forgot to mention implicit differentiation in the last video. So if you need to recall exactly what implicit differentiation is, please do look on page 294 for the steps of it. And otherwise, what I do hope is I'm going to just do this example number 21 from your homework and hope that it can kind of refresh your memory just by doing it in this example. So implicit differentiation, when we look at the word implicit versus explicit, if you have an implicit statement, it's something that's kind of implied. It's like the truth is hidden amongst things that you could say that's not just the full out truth. So same with implicit equations, what we have is this y versus some sort of equation where I would just say straight up y is equal to this, and it would just be something very frank and very explicit what y is equal to. This is what we would call an implicit equation because y is kind of hidden amongst all this garble, I guess. So when we're trying to differentiate this, we're actually not going to solve for y and then differentiate. We could, but sometimes that doesn't always work real pretty, and it wouldn't for this. So what we're going to do is leave it in the state that it is in, this implicit equation, and we're going to derive. So the first step for this is to actually derive both sides with respect to x. And I am going to say we are deriving this with respect to x. So the one thing we have to watch out for is because we've left this as an equation of both x and y, we have two variables in here. E is not a variable, by the way. I did not mean to say that. E is a number. But x and y are the two variables, so we need to watch out when we're trying to derive this with respect to x. I am going to go ahead and break this down because we do have a rule that states that we can just differentiate term by term if the terms are separated by subtraction and or addition. This very first one, I hope you can see, unfortunately we have this multiplication symbol here. So we do have what we call the product rule. Unfortunately we can't just derive x and then derive e to the y and multiply those derivatives together. What we actually have to use is the product rule. So I am going to begin by saying this is x times dx, and I haven't derived it. I'm not going to derive anything just yet. I'm just going to set myself up for driving, and then I would have to go back and derive my first multiplier, and then times. I would leave my second one alone this time. I'm sorry, I am going to do this and differentiate. If you have minus the derivative of 10x, this is x to the 1. You bring down that 1, drop this to be 1 minus 1, so it's going to be x to the 0. So that x drops out. So if you can kind of, I know we're going back and forth between integration and differentiation, but we're going to have to keep those straight. So here we're going to be looking at this. Now here I have a small issue. What I have is this function y, and when I'm deriving y with respect to x, we have to use the chain rule. So we have to assume that this is some sort of function going on. We can go ahead and say 3 times the derivative. So we can go ahead and pull this 3 out. But we are going to have to focus on the fact that we're going to try to derive y with respect to x. And we can't just do that. Had it been just x, we could have said it's going to drop down to just be 1. The derivative of x would just be 1. So, however, this is going to be, we could derive this outer function and y would drop down to be 1. But then we would have to go in and drive the inner function to be dy dx. We don't know what the derivative of y is with respect to x, so we actually have to just call it dy dx. So here I'm going to start deriving now. I've derived nothing except for I guess this term right here, but I'm going to have to go through with these ones. So we have x times the derivative of e to the y. Now once again we're deriving with respect to x, so this is going to be e to the y left alone, but then we would have to go in and say, but then we would have to take the derivative of y with respect to x. So this is how it would be. Plus, the derivative of x with respect to x would just be 1. Okay? And then times e to the y, so it's just going to be e to the y. Sorry, I'm going to just cover that. Alright. Minus, we have our 10, plus 3. Here we go with this. I mean, the outer function would just be 1, but then we would have to go in and then multiply by the derivative of y, which we could notate as just dy dx, and then equals 0. Alright, so in this stage now I'm going to pull all of these terms this term right here and this term to one side of our equation. Oops, this is part of it. So we're going to have x e to the y dy dx, and then plus 3 dy dx equals, and I'm going to subtract this off and I'm going to add 10. So I'm going to get, I'm going to actually say 10 minus ey, because I subtracted e to the y and I added 10 to the x. And it's because I have all of the terms with dy dx on this side, I can pull that out. There is a factor of dy dx in everything on this side, so when I pull that out, I'm going to get dy dx, and then in parentheses I would have left x. Alright, and since I want to just figure out what is the derivative of y with respect to x, I can get this by itself now to solve for it, get this notation by itself. So this is going to be divided from both sides, and there is our answer. dy dx, so the derivative of y with respect to x is equal to this right here. What we're about to do is we're about to integrate now the exponential base e. Now what we're going to do is integrate. So these are some of those old basic rules of integration. We only have 5 of them, so keep them straight. One that I do also want to bring up is that if you ever had the integral of some sort of composition function, so f of u we'll call it, and what you had was the derivative of that inner function, whatever it may be, what this would just be equal to is you would antiderive that I guess what we would call it is just that function, and that du would disappear, so it would just be f of u plus c. Okay, so one example of that is if you ever had something like x squared plus 1 square rooted, what you would hope is that you would have something like this, 2x dx on the outer side, because if you had that, you could say, well, u is this inner function, u x squared plus 1. Okay, and then du dx is going to be, well, that 2x, and then I could rewrite this as 2x dx, so du is equal to 2x dx. And what would happen is I could rewrite this as u to the 1/2, and then times du, and then we could just integrate this like normal, just integrate this function right here, and then drop that du. So we would get u to the 3/2, so we're going to add 1 and then divide 2/3. Okay, and then we would go on la-di-da, adding, subbing back in for our u. Okay, so here are the 5 basic, but then don't forget, if you ever have a composition function going on, integrating that took a little bit more of work, which we called u substitution. So now that we're going to be integrating these exponentials base e, what we should look at, because integrating is anti-differentiation, or in other words, doing differentiation backwards, where we should look is at the derivatives of these functions, because then we can work backwards. So I'm going to have you take a look at this one right here. One way to write this is if we had y is equal to e to the x, what we could say is, well, then the derivative, I could notate it in this form right here, the derivative of y with respect to x is going to be, this one's an easy one, the derivative of e to the x, which we stated was this right here is just e to the x. So we have dy with respect to x is equal to just e to the x. It's the one function that does that. So what we can do is rewrite this as a differential, which means I would just multiply dx to both sides. These would cancel out, and what multiplying dx to both sides is, it creates this equation that we call a differential, and it stamps this expression right here as a derived equation. It expresses that this is an equation that's been derived. So now that I know that this is an equation that's been derived, if I want to go backwards and figure out what I had in the beginning, well, we're going to use this notation right there, and this is the integration symbol, which would say, all right, well, if I'm going to take a derivative of y and undo it with that symbol, then what we're going to have is y is equal to, and luckily for us, this is what you're going to have to recognize. If you're ever integrating e to the x with respect to x, then it's just going to be e to the x. Alright, over here it's not so simple. We're going to have to use that chain rule effect, because here we go. If you ever had, I'm going to do an example, one that we've worked with. So here I'm going to derive it. And what I'm using is this right here. My u is equal to 3 to the x, or I'm sorry, 3 times x, and then du dx is just equal to 3 when I derive my u. So I'm going to have to derive that inner function and multiply it to the whole derivative of the outer function. So my outer function is that e to this u, and that's just going to be left alone. So dy dx is equal to e to the 3x times, and then I have to go in and then multiply it by this inner derivative. Sorry. So here we have it. We're going to now write this as a differential. I'm going to say dy is equal to, when I multiply dx to both sides, I get e to the 3x times 3 dx. This is something that's been labeled a derivative. So when I integrate this to work backwards, what I have to hope for is, because this is a composition function, I'm going to have to acknowledge that that exponent right there is a function in itself. So I would have to, once again, if you look at over here, it's going to be that same technique. Well, I have this u equaling 3x. Okay, and what I'm going to hope is, because of this integration process of a composition function, what I need to do is resubstitute in, or substitute in for all of these x's a u. So I'm going to have to come up with an equation that relates x's with u's. I've done that here. But I'm going to have to come up with an equation that links the dx with the du. So therefore, I'm going to have to actually derive, in this process of integration, I'm going to derive this inner function that I've acknowledged, and I'm also going to write that as a differential. So I get 3 du is equal to 3 dx. And that's what I would hope for, that I can replace any kind of inner function. And that's what I'm going to hope for, that I can replace all of my x's and dx's with the relationship of du or u. So here, those cancel each other out. My original function would be this. E to the u, oh, I have not integrated it yet. So e to the u, and then here my 3x dx goes out, my du comes in. And this right here is going to lead to that whole composition piece, that here I just have an f of u function, so I just need to integrate this. And this integration, this du will drop, so will this symbol, because what we're just going to be left with is its original. So we're kind of looking at over here. So y is equal to this original e to the u, and goodness, I forgot my c over here because it was an indefinite integral that I did. But here what I'm going to do is get the same type of deal. It's just going to be e to the u, and what I need to do finally is resubstitute in that 3x. Okay, so here we're going to look at our two new rules. Two more rules of integration. When we're looking at exponentials, base e, you're going to have to watch for, if you have e to the x with respect to x, then it's just going to resort back to what it was, e to the x plus c. If you ever have an integral of e to the u du, then easy for us, it's going to be e to the u plus c. But the one thing is that's going to happen when you're writing these composition functions, you're going to have to replace all your x's and all your dx's with these u's and du's, and that's going to be the challenge. The integration problems really start to begin at around 45. They ask us to integrate. Okay, they give us this integration problem. And so what you need to look at is that I don't have just simply e to the x here. I do have some sort of function going on as my exponent, so I am going to identify that as u equals 5x. I'm also going to look at du with respect to x. I'm going to derive my inner function that I've observed and then call that 5. So du, when I write that as a differential, I get du is equal to 5x. So here what I can do is out with this, the 5x, in with the u, okay, out with this 5 dx, in with what it's equal to du. So this right here is simply, using our new rules, e to the u plus c. And all you have to do is plug back in what is your u, 5x plus c.